In 9.3, we're going to look at vertex colorings. A proper vertex coloring is one in which all vertices are assigned colors in such a way that no two adjacent vertices have the same color. And if a graph can be properly colored with K colors, then we say it is K colorable. So looking at our example from before, let's just jump back up here. Going through and assigning colors. So we've already got black. We'll just use that as one of our colors. I can make this one blue. I can make this one over here blue. I can't use blue there. I need at least one more color. I can put, say, a red vertex there and a red vertex over here. So this graph is no more than 3 colorable. And because we have a cycle of length 3, for instance right here or right here. So we'll see later on if we have K something as a subgraph, then we're going to need at least that many colors in it. So we need at least 3 colors here. Now we could have more than 3. For instance, if I put a violet colored one there and maybe I make this one green, I can have as many colors as I have number of vertices. So the K value is up to the number of vertices. Now the chromatic number of a graph, denoted by chi of g, is the least number of colors needed to color the graph. So in this case, chi of g was equal to 3. I didn't need all 6 colors to form a proper coloring of that graph. So we can use graph colorings and the chromatic number to solve what are known as conflict problems or scheduling problems. So in one example, let's say that we have 3 classrooms available for giving makeup exams. 5 students need to make up exams for 7 different classes. Sheldon needs to make up exams for courses 1, 3, and 7. Elvira for courses 2, 4, and 1, Irma for courses 2 and 5, Geraldine 1, 4, and 6, Josephina for exams 3 and 5, and we want to know what's the minimum number of time slots needed in which to give the exams. And would that change if there are only 2 rooms available or 5 rooms? Does the number of rooms even matter here? So we're going to go ahead and start drawing our graph. We're going to have 1 vertex for each of the classes because a student can't take an exam for the same class simultaneously. So we're going to have something like this. And then we're going to draw an edge if there is a conflict between those 2 vertices. So in this case, a conflict would be a student needing to take both of those exams at the same time. So in this case, we would have a conflict if a student were told that they had to take the exams at the same time. So Sheldon needs 1 and 3, so we're going to draw an edge there. And then between 1 and 7, and between 7 and 3. Elvira, 2 and 4. And 1, so between 4 and 1, and then also between 1 and 2, so we're going to have all those possible combinations. Irma, 2 and 5. Geraldine, 1, 4, and 6. So we already have the 1, 4 noted in there, so 1 to 6, and between 6 and 4. And then Josephina between 3 and 5, which we didn't already have. So we're going to go through and then find a coloring of this graph. We'll use black as one of the colors. So I'm going to need, say, red here. We'll put red there. And over here, I'm going to now need a 3rd color to finish the coloring. Because I have this black vertex adjacent to red, and 7 and 3 are also adjacent. I couldn't use red there. So I'm going to have to use blue on that one. And then down here with 4, because we have 1 and 4 connected, and 4 is also connected to 2, and 1 is connected to 2, we have that cycle of 3 vertices. I'm going to need a 3rd color there for that. So this tells us that we're going to need 3 different exam times. And we'll assume that the students can take the exams in the same room. If that's going to be a restriction, then we'll adjust that in a minute. So let's look at the exams that need to be scheduled at the same time. So anything with the same color can be in the same time block because we're not going to have a conflict. So the blue vertices, no one needs to take both 7 and 4 at the same time. So those exams can be going on simultaneously. Now, do I need to have all 3 classrooms? Well, it depends. If I'm going to be giving exams in the same classroom for different exams, then I just need 1 classroom for each of these times. If we're trying to keep people separate, so all the people taking exam 4 are going to be in one room, all the people taking exam 7 are going to be in another room, I'll need 2 separate classrooms available at that time. I'll need 2 separate classrooms at time 2, and I would need 3 separate classrooms at time 3. So what would change if only 2 rooms were available? Well, in that case, I would need, say, a 4th time slot for one of exams 2, 3, or 6. That one's going to have to get moved to a different time slot. If 5 rooms were available, well, that doesn't really change anything. I'm not able to reduce the number of time slots because of the chromatic number, and so we would still need those 3 time slots, but the number of rooms doesn't really matter there. Once we get above 3, since we need to have 3 exams running simultaneously, if there were only, say, 1 classroom available, again, as long as I can give 2 different exams in the same room, then that would be fine. If we only had 1 available, though, and they couldn't be given simultaneously in the same room, then I would have to have 7 different time slots. Let's look at another scheduling type problem, this one taken from the book. We're going to look at exercise 9.3.10. Which is this one. We have radio stations. 2 radio stations need to be assigned different frequencies if their broadcasting locations are within 120 miles of each other. How many different frequencies must be used for the 7 stations whose distance are shown in this table here? So I'm going to go ahead and bring this table over into the file so I can reference it as we're talking through it. So we're going to have vertices for each of the stations, A through H. And then we're going to go through and look at distances. I really only need to look at the upper diagonal here, and we're going to draw an edge between those if we have a value that's greater than the value listed in the problem, which was 120. So they'll need different frequencies if they're within 120 miles of each other. The conflict here is being within 120 miles of each other. So we'll draw an edge if that condition is satisfied. Again, we just need to focus on the upper diagonal here and look for the ones where we have a distance greater than 120. So between A and B, we have a value less than 120, so we're going to put an edge there. We don't need one A and C. We do need one between A and D, between A and F, and that's all for A. Looking at B then, we need an edge going now to C, to D, and to F. And then they said within 120 miles of each other, so we'll go ahead and put one between G and B as well. And then moving on to C, we need edges going to D, E, and G. And then D, we'll need edges going to E, F, and G. And then from E, we need an edge going to F, G, and H. Looking at F, we now need an edge going to G. And then at G, we need an edge between G and H. So there's our graph. We'll go ahead and see how many colors we need. So let's start with D, since it has the largest degree. Now D has degree 6. So let's start putting in colors. We'll leave D in black, and we'll see if we need additional colors. So I'm going to have at least one other color. D and C are adjacent, so we'll need a color there. We'll use that purplish brown color. And then D and B are also adjacent, but because B is adjacent to C, I'm going to need a new color there. And then D and A are adjacent to each other, and then A is adjacent to B, but it's not adjacent to C, so I can go back to using that brown color. D and G are adjacent, and then G and C are adjacent, so I can't use the brown. I'm going to have to go back to, say, red for that. And then D going to E, well, that's adjacent to both C and G, so I'm going to need another color for E. And then D going to F, I'm going to need another color there. I can't use red or blue because those are adjacent colorings, but I could go back to the brown color there. So put that in on F. And then let's go ahead and check, make sure that H is okay. H is not adjacent to D, so I can leave that black. And the colors to which it is adjacent, the G and the E, are already different from that. So looking at the chromatic number then of this graph, chi of G, we ended up using 4 different colors to color it. So we should be able to broadcast with 4 different frequencies and not have any conflict because of the distance between them. So a theorem related to the chromatic number, if we have at least one vertex, then the chromatic number is going to be at least 1. If we have at least one edge, then the chromatic number is going to be greater than or equal to 2, because the adjacent vertices are going to need different colors. If we have a bipartite graph on at least 2 vertices, then the chromatic number is going to be less than or equal to 2. Remember, bipartite means that we're going to have 2 sets of vertices. We can partition them in such a way that for every edge, one of the endpoints is in one of the sets and the other endpoint is in the other set. So for instance, here, if I have those 6 vertices and choose to group them in that way, if I don't have any edges, then I have a chromatic number of 1. I can color them all the same color, leave them all black, and it doesn't matter. And here, the way that I'm partitioning them, there's nothing special about that. I could, since I don't have any edges, I can do whatever grouping I want. So I could make those my partitioning sets. But once I start drawing edges between these, then I'm going to need different colors. So if I keep that as my partitioning set, we could have red here and black over here. I could have additional edges from the black into the red. They have the same color. We do something like that. That wouldn't be quite K51 because I don't have the edge here. But if I do that, then we end up with our complete graph on a partition where one set has 5 vertices and the other has 1 vertex. But bipartite graphs, as long as we have at least one edge showing up, then the chromatic number is going to be equal to exactly 2. If we have the complete graph on n vertices, then we're going to need n different colors. So up here, we were using that fact when we had a 3 cycle. Got 3 vertices, drawing all possible edges between them, then I'm going to need at least 3 colors for that. And I can't have more colors than the number of vertices, so I'm going to have exactly 3 colors being used there. So as we're looking at a graph, if we can identify a particular kn as a subgraph, then we know that we're going to need at least n colors to color that graph properly. If we have a cycle on n vertices, then we're going to have a chromatic number of 2 if n is even, and 3 if n is odd. So for instance, this is also C3. I'm going to need 3 colors there. If we draw C4, we're going to have our 4th vertex. Put that right there. Then I could get away with just 2 colors in the coloring. I can have red here, for instance, and here, and then we have a properly colored graph. The dual graph of a map is the graph created by representing each region of the map by a vertex. So for instance, if we look at this map of the United States, if I want to create its dual graph, then I'll just look at part of the graph. I'm going to go with the actually, let's not have quite so many drawn in. Let's just look at these particular states so I don't have too many edges showing up. We're going to represent each region with a vertex and then place an edge between the vertices if those regions share a common border. If they're just touching at a corner, then that's not going to be considered a common border. So for instance, here between Idaho and Wyoming, we'll have an edge, Idaho and Nevada, Idaho and Utah, and then to Wyoming and Colorado, Utah and Colorado, Arizona. I guess Nevada and Arizona needs an edge too. We're not going to need an edge between Utah and New Mexico because they're just touching at a corner there. So we're going to end up with that dual graph if we're just looking at those states. And a graph is planar if and only if it can be drawn in the plane without any crossing edges. And if we're looking at a dual graph, then that is always going to have a planar representation. And then the theorem, the four-color theorem, is that the chromatic number is less than or equal to 4 if G is a planar graph. So looking at our graph here, we're going to need at least 4 different colors because we have this 4 cycle. So let's go ahead and start coloring in this graph. If I do, say, red there, then I could use, let's color that 4 cycle first, and then we'll figure out what we want to use on the rest of them. So we've got those 4 colors, and then we'll just make sure that we've got all of these other adjacent vertices taken care of. So I'll use something different there. Let's use blue on that one. Those were supposed to be different colors. Let's highlight that a little bit more. There we go. So now we don't have any adjacent vertices with the same color. And you'll notice in this particular map of the United States, there are only 4 colors used to color the states in such a way that no 2 adjacent states have the same color. Again, not counting touching at points there. So we've got the yellow, green, purple, and brown being used as the colors here. And so any map is going to be 4 colorable. Planar graphs, we'll look at those more in later sections, but briefly here, let's just look at an example of why it's 4 colors and not 3. So look at W4. Let's go ahead and draw that. We're going to have our 4 vertices here, and then edges like so. So we already have a cycle of 3, so we're going to need at least 3 colors there because of the outside edges. So let's go ahead and color those in and then see what happens with the center vertex. I'm going to need red there, for instance, and blue over here. But now I have these 2 black vertices adjacent, and I can't use blue on the center because it's adjacent to the blue one over here. I can't use red because it's adjacent to the red one up there. So I am going to need a 4th color for that. And let's try to use something that'll stand out a little bit more. We'll use green on that, say. So I do need 4 colors for W4. I can't get by with just 3. This is a planar graph. It doesn't have any crossing edges. I've drawn it in the plane in 2 dimensions without any crossing edges. We'll look at planarity more later on, but let's look at a fun example of planar graphs right now. If you go to planarity.net, you'll come to this. I'm going to play in the small window because I'm trying to record in a small window. And it'll give you a graph, and the goal is to make it planar. So I'm going to take this and just move things around until we don't have any crossing edges. And then when we're done, click on the check mark, and it'll tell you whether or not you've solved it correctly. So for this one, I'm just going to move some things around here. And watching this later, I do have some more vertices that are off screen here. Let's see if we can get that in. There we go. Move that around, bring this one over here, and then that should do it. And then you can jump to a level if you'd like. Let's go ahead and do that. So you want to skip to level 20. Well, it's going to become rather difficult to solve at some point. Let's see if it can handle it. And it crashed. So there are only so many levels that you can get up to. Anyway, so you can play around with that. Oh, there, I had at least some of it drawn in there. And we'll look at planar graphs more in the next section.